today I have a demo that doesn't have any slides. I just have one architecture diagram, and then I'm going to walk you through an end-to-end demo. I'm actually VPNing into my lab in Hyderabad to show you this. It's a slightly risky and stressful demo, but hopefully it works. Because of the GPU shortage, it's extremely difficult to get hold of a GPU cluster in the cloud. So I invested in building my own GPU cloud in my lab, and I'm going to use that for today's demo. So what am I going to show you? Well, before I really talk about that, let me ask you a few questions. So how many of you are familiar with Kubernetes and use it in your day job? Oh, fantastic. Okay. How many of you are familiar with LLMs and built a RAG prototype or an early demo? Okay, quite a few of you. Okay, so most of us, when we consume generative AI, we consume it through APIs, right? You go to OpenAI, or you go to Azure OpenAI, Google Cloud, or Amazon Bedrock. Those are some of the popular destinations, popular endpoints from where you consume generative AI. But as generative AI matures, we are going to see adoption of this technology by enterprises, which means it is going to move from the cloud to on-prem. So a lot of customers are going to run generative AI infrastructure within their data centers on premises. Of course, there will be some cloud deployments, but given that the majority of the data lives within the data center on-prem, it makes sense for enterprises to run their own GenAI infrastructure, GenAI platforms, and GenAI applications. So obviously, the choice for running these new breed of workloads is going to be Kubernetes, because Kubernetes is a proven workhorse for running scalable, reliable, and highly available workloads. And for running GenAI workloads, Kubernetes becomes the de facto choice. So if that is the infrastructure, how do we go about building this stack? So just like you build a stack for your application based on infrastructure, we need to assemble some of the open source components, some of the proprietary components to build our own platform. For example, when you are building a web application that is hosted in Kubernetes, you need a web server like Nginx or Apache. You need a database. You are going to bring an API server. You are going to bring a cache server. You will assemble all of these containers as microservices, deploy them, and then run them in production, monitor them, and manage them. So very similar to that, the generative AI stack is going to be assembled from a set of open source components that are going to be deployed on Kubernetes to deliver the platform experience to developers through APIs and through a variety of other experiences. Now, what is the top use case of generative AI for enterprises? Well, there is something called retrieved augmented generation. And I want to spend just a minute giving you a glimpse of what it really means. How many of you are familiar with this term called RAG? I'm asking it again. Okay, only 10%. So I'm going to spend just a few minutes explaining you what is RAG, and then we will take a look at the demo. So how many of you use ChatGPT? Okay, how many of you told your manager that you are using ChatGPT? Okay, so so ChatGPT, it is becoming like the go-to application. There are millions of users already using ChatGPT, but as you would have noticed, there is a significant problem with ChatGPT and large language models. They are only knowledgeable up to the cutoff date based on their training. So many of the times when you ask a question to ChatGPT, you would have seen an answer something like, sorry, my training cutoff was January or September 22, so I don't know what you're asking, I cannot respond to your query, right? So how do you bring context into ChatGPT so that it can really respond to questions very intelligently based on your data? Assuming you have a data warehouse, assuming you have a SharePoint portal. Now, your financial data, your annual reports your sales forecast, your CRM, all of those are running on-prem, and you want to bring data from these into a chatbot like ChatGPT so that it has access to grounded data and can respond with factually correct answers. So when you bring the context along with your prompt, and actually just like you ask a child, given this paragraph, answer this question, if you ask an LLM based on this context, answer this question, it can come back with factually correct data. Now, augmenting the prompt by adding context is what is called as retrieval augmented generation. It's almost like comprehension that we have done in your high school, where you basically read a short story and then you answer a set of questions based on that story. Now, that story in the context, in the world of LLMs, is actually called as the context. And this context will come from a variety of data sources. It can be a NoSQL database like MongoDB. It can be a relational database like MySQL. It can be a data warehouse like BigQuery or Snowflake or your traditional data warehouse. Or it can come from unstructured data living in your NAS or in an Amazon S3 bucket. You have to connect the dots, create this context, and pass it along with your prompt so that the large language model is factually answering the questions instead of hallucinating or instead of coming back and telling it doesn't know what you're talking about. So this is called RAG. Now, RAG is typically built with a set of components in the cloud. There are vector databases. That's a new breed of databases that can store semantically contextual vectors. I don't want to get there, but think of this new breed of database, which is the vector database, and there are multiple sessions at GITS. You can actually follow along some of those. But basically, you go back to a vector database, perform a query by sending a vector, and based on an algorithm like a cosine similarity, the vector database will retrieve all the vectors and sends it back. And then these vectors are matched against the original data, which is the metadata, and that is used to inject the context. So this is a slightly complex concept, and it can become very, very involving by bringing multiple components like re-rankers and a lot of stuff. But I don't want to get there. But how do we build a RAG application on Kubernetes without consuming from the cloud? So I want to show you a live demo. Can you see my screen? Is the font and the text visible? Okay. So what I want to show you is something called as an event-driven RAG. So event-driven RAG is as soon as you add data to a data lake is the repository of your unstructured data like PDFs, Word documents, JPEGs, and so on. As soon as you add data, your chatbot instantly becomes aware of this and comes back with factually correct responses. So my entire demo is built around a fictitious airlines company called Redjet Airlines. And our goal is to build a co-pilot for passengers to assist with their queries. But currently, this chatbot has some context, but I'm going to remove all the context and then build from the scratch. So I have one of the queries here. This is a query related to what is the excess baggage fee. Now, when I actually run this query, you can actually see that my chatbot comes back and says, I don't know, the context doesn't provide enough information about excess baggage fee. Now, I want to show you a PDF. Okay, so we have a PDF, and this PDF, actually let me open V1. So this PDF actually has some data. This is the baggage policy of the airlines. So Redjet is a low-cost airline. It's a PDF that customers can download, or it's available on the Redjet Airlines website. And specifically, the highlighted text says 25 euros per kg for domestic flights and 20 euros for international flights. Oversized baggage fee is 45 euros. Now what I'm going to do is I'll come to the command line, and I'm going to basically add the V1 of my baggage policy into my data lake. So now I add this, and I come back to the same chatbot and ask exactly the same question. What is the excess baggage fee? Now, it comes back and precisely tells you that it is 25 euros per kg for domestic flights and 20 per baggage for international flights. So it instantly became aware of the data. Now, what we'll actually do is we'll open V2 of this document. Let's say the airlines has decided to increase the baggage fee. So now they have increased it from 25 to 30 for domestic, 20 to 25 for international. So what I'm going to do is now I'm going to copy the V2 policy, baggage policy, to my data lake. And then I come back to the chatbot and ask exactly the same question. So now you actually notice that it instantly picked up what I sent. And if I remove, for example, if I remove my baggage policy document and ask the question again, it goes back to the original statement that I don't know what you're saying. Now, this ability to put data into a data lake and instantly making your chatbot aware is what is called as event-driven RAG. So event-driven retrieval augmented generation, where you don't have to wait for the data to become available. Of course, if the data is large, then the strategy is not ideal. You should make it asynchronous. But this is what currently is running in my lab. So if you actually see, I connected to my VPN, and now I want to show you the architecture of how this is being done. So let's take a look at the architecture. I'll take the questions towards the end. So this is my Kubernetes cluster. You don't see that. That's the powering infrastructure. So I add a PDF to what is called as Minio or MinIO, right? MinIO is an S3 compatible storage engine that is very powerful. And just like Amazon S3 supports events that trigger a Lambda function, MinIO supports triggers as well. Now, to keep this simple, I created a webhook which is going to be triggered when the event takes place. And the event is either uploading the document or removing the document. Now, as soon as the event is triggered, what I basically do is I chunk the document into multiple pieces. So, for example, I chose sentence-based chunking strategy. And for every sentence, I generate an embedding. Now, this is a very important step because embeddings are semantically representing your data, your text, without losing its meaning. It's not a full text search, but when you store embeddings and perform a search, the similarly structured data or data with similar meaning is retrieved, not based on the keyword. And how does it happen? You basically encode your data into a set of vectors. You store those vectors. You also encode your query into the same embedding, put that as a vector, and then you search that vector against everything that is stored in the database, and certain vectors are retrieved based on the similarity, and then it comes back with the actual response. So for that, I chunk the baggage policy document and then convert that into embeddings, and I store all the embeddings in a database which is called as Chroma. Chroma is a vector database. It's a new breed of database designed for semantic search, for indexing, storing, querying vectors. So once that is done, then I have the chatbot written in what is called as Gradio. So Gradio is a framework to develop chatbot UI. So I built a Gradio app, and my LLM is Mistral 7B. That's all I can run on my consumer grade GPU cloud. So I'm running Mistral 7B. So as soon as a query is input, that query is sent to the embeddings model. We vectorize the query, and then we perform a search in the ChromaDB for similarity. And ChromaDB comes back and gives us data in a ranked order. We pick up the top K, maybe 2 or 3 sentences that came out of Chroma's query. We embed that as a context and send that context to Mistral, and now Mistral gets empowered to respond accurately based on your query. So this entire architecture is run on Kubernetes. So now let me switch gears, and for the rest of the demo, I'm going to only show you a bunch of YAML files. So be prepared, but I'm going to walk you through what it takes to build this infrastructure from the ground up. If you have access to a Kubernetes GPU cluster. So I have exactly one node. This is called my Gen AI testbed. This is running 800 kilometers away from where we are in Hyderabad, and I have VPN'd into this. So now what I'll do is I'll basically SSH into my test bed to show you what this is. So this actually runs a pretty powerful CPU. It's an i9 CPU with 32 cores, 14 gen, fairly powerful state-of-the-art CPU. That is my core processor. And then I have two GPUs running in this box, GeForce RTX 4090, and currently you see that one of them is barely consumed, only 10 GB, or no, not even 10 GB, I think it is just 1 GB of memory is consumed, and the remaining GPU has 100% utilization. So this is the LLM, which is running Mistral, and this is running the embeddings model. So I have two GPUs to run my models, the embeddings model and the actual LLM. And then I have 128 GB of memory. So this memory is very important when I'm actually fine-tuning, apart from having the VRAM of the GPUs. So I have 128 GB of RAM and 4 TB of storage. So if you actually look at my disks, these are the disks. So altogether, one is not visible, but altogether I have about 4 to 5 GB of storage, hot swappable, attached to this machine. So it's a fairly powerful machine, and on top of that, I run Kubernetes. So if you look at the Kubernetes version, I'm running a slightly older version. I've been running this box for a while. I just came back from a long trip to Europe where I demoed this in multiple places, including KubeCon Europe in Paris a month ago. So I've been running this box with sufficient cooling for the last 1 month uninterrupted. So, so that's my infrastructure. Now, where do we go from here? Well, let me first undeploy what we have so that I can actually walk you through the entire process of building this stack. So there are a lot of considerations that you need to make when you are building this. So, okay, now maybe this is the time for me to take exactly 2 questions. You had a question. Okay, okay, got it. The question was about the databases, and I had it covered in this slide. Perfect. So let's go ahead and deploy this stack step by step. And in that process, I'll explain some of the design considerations and the architectural choices I made. So it all starts with the namespace. So let's first deploy the namespace. Currently, if you look at my namespace, I don't have the stack running, but I need to start from there. But before that, let me also give you a peek into my software layer. So obviously, this is running CUDA, NVIDIA CUDA version 12.3, and I'm also running Docker, the most recent version of Docker. And what I did is I also installed what is called as NVIDIA Container Toolkit. So what Container Toolkit does is it basically makes the GPUs available to your containers. So if you actually look at my Docker daemon.json, it actually says that the default container runtime is the NVIDIA container runtime. Now, what this basically means is when you run containers on top of Docker, it has a pass-through to give you access to the underlying GPUs. So I already configured this. And I also installed PyTorch, TensorFlow, and created my test bed independent of Kubernetes. What I actually do is I keep the models and the data sets on a well-known location in my machine. And this location is basically HF, which is Hugging Face. So every time I download a new model from Hugging Face, it actually lives in this directory. Now, the reason why I do this is I basically access my models from three different environments. First environment is I fire up Jupyter Notebook and I directly consume a model and I play with it interactively. So my Jupyter Notebook needs to have access to the model and needs to have access to the GPU, and it is running non-containerized, non-virtualized straight on my host. That is one environment. The second, every time there's a new model and every time I want to play with something new, I prefer Docker. So I also need to access these models from Docker. So when I actually launch a Docker container, I point the volume of Docker to this directory so that when I am using, for example, Llama 3, I don't download that every time I fire up my Jupyter Notebook or a Docker container. They all share the same model catalog that I keep this in sync. I have a cron job that actually keeps this in sync. Every time there's a new revision on Hugging Face, my cron job will pull the latest revision and synchronizes my local model catalog with Hugging Face. So this is a centralized model repository for me that's always in sync with Hugging Face. So that is a very important consideration. So Jupyter Notebook, Docker, Kubernetes, all of them share exactly the same directory on my host machine. So with that, let's go ahead and create some of the steps. So I want to use this deployment script. First, I'm going to deploy the namespace. And this namespace obviously is going to be empty. We don't have anything. And once we have the namespace, I'm going to deploy what is called as config map. I'm sure all of you are familiar with a config map. It is my settings. This is where I define my endpoints. For example, Minio server lives at a cluster IP called storage on port 9000. These are my access key and secret key, the defaults. I also have a webhook, and I mentioned why I need a webhook, basically to vectorize my PDFs that I'm going to upload. And then the Minio bucket name is called PDFs. ChromaDB is called VectorDB. The embedding server URL is this. This is the LLM URL. The collection in the vector database is called PDFs. So all of those settings are basically defined here. So now let's go ahead and deploy that. So we will now deploy the config map into our namespace. So now that basically sets the stage. We have all the declarations and initialization values available here. Now, once we have these two, it's time for us to deploy the LLM. Now, this is the beast. This is actually the brains of the application. So currently, when you look at NVIDIA SMI, both my GPUs are unutilized. They don't have any models running. The proof is you actually see that only 2 GB is consumed, or 2 MB, sorry, 2 MB is consumed out of these two GPUs. So our goal is to deploy the LLM, which is Mistral 7B on Kubernetes. So what I'm going to do is first I'll define a PV, a persistent volume. And for this, I'm actually using a storage class name called local storage. So local storage is a very useful and a powerful storage engine, a CSI based storage engine from Rancher, local path. So I use that to point my Kubernetes application to the same model catalog, model repository. I have it on my host machine. So how do I do that? When I'm defining my persistent volume, I am giving the path to OPT data HF hub. And if you actually look at that, that's exactly where I store my models. So that's where I make the connection between my workload and the local model catalog. Now, once that is done, I define a token because I need this to pull images, sorry, not images, but the models from Hugging Face. So Hugging Face model repo. So once I do that, then I use a very powerful inference server from Hugging Face called TextGen Inference. So if you are using a commercial version of Hugging Face for serverless inference, apparently they use exactly the same container and same inference server. So I'm using the same thing. This is an open source inference server. This is used by a lot of companies, including Hugging Face themselves. So for that, I actually send my model ID, which is Mistral AI, and I copied and pasted this from Hugging Face model catalog, and that is exactly what is available here. So models, Mistral AI, Mistral 7B, instruct 0.2. So that's exactly what I'm running. And then I define the limits to one GPU. I don't want this to hog both. Sometimes you never know. Uh, if you don't really mention this, and if you have like a framework that enables distributed inference, it might even occupy more than one GPU. So to confine it, I'm actually providing my NVIDIA GPU count to 1. Now, at this point, I want to call out a very important aspect. So what happens when you deploy the GPU operator or the GPU device plugin from NVIDIA? So I run what is called as NVIDIA device plugin, and when you look at all the pods in the NVIDIA device plugin namespace, you actually see that there is something called GPU feature discovery and NVIDIA device plugin. So these are very critical components that make Kubernetes talk to the underlying GPUs. So we have already seen the NVIDIA container toolkit, which acts as the glue between the GPUs and containers. Now, taking it one level above to Kubernetes, you need the device plugin. So I installed the device plugin, and what it basically makes is the GPUs becoming visible to my Kubernetes cluster and subsequently to the pods. So now when I actually do kubectl describe nodes, you actually see that this device plugin has added a lot of labels to my Kubernetes cluster, to my Kubernetes nodes, to be more precise. And one of the label is nvidia.com GPU count is 2. Now that means my pods can actually decide or request how many GPUs it can consume based on this feature discovery capability. Now, based on this, I'm actually saying give me 1 GPU. And it also calls out the product NVIDIA GeForce RTX 4090, that is my GPU model. GPU family is Ampere. So it comes with all the metadata that you can actually use in your node affinity or your scheduling to choose precisely where you want to place. For example, in my cluster, if I have one A100, a Tesla T4, and a consumer grade 4090, this is where I can actually tell that. Now I can grab this label and I can actually say GPU product is equal to A100 or T4 or 4090, and Kubernetes scheduler will automatically place my pod on the target node. So that's very important consideration. So here I mount data, and data is coming from here. If you actually see, we define the PV and PVC here. So when we actually look at the volumes, so data is coming from this PVC, and this is where the models are going to become visible. I also have shared memory that is set to 1 GB, and then I have a service, and I put the static IP to 10.10.10.3. So now it's time for me to deploy the LLM. So now let's go ahead and deploy the LLM. Now, as soon as this is done, let's take a look at the pods. Now the LLM is running, and now when we go back and run NVIDIA SMI, you notice that this is picking up. Yeah, there we go, 100% utilization. So the LLM has now successfully launched, and its weights have been moved from disk to GPU's VRAM. Perfect. So now the LLM is up and running. I can even take a look at the logs to see what it is doing. So kubectl logs, and it shows it's currently running. So all good. We don't have any errors. A couple of warnings, that's fine. So that completes the first very important step. Now once the LLM is running, the next is launching the embeddings model. And I briefly mentioned why we need an embeddings model. So embeddings model is the actual translator or the gateway of the LLM. Now it takes text and converts that into a set of vectors, a one-dimensional array that preserves the contextual, the semantic meaning of the text. So, for example, if you have news headlines of multiple sports, like cricket-related news, football-related news, and you want to retrieve all the cricket-related news, if you actually send ball, the semantic meaning is almost the same. It will pick up the vectors that match both football and cricket. But if you actually send Sachin Tendulkar or Virat Kohli and then do a semantic search, the embeddings model is smart enough to say, oh, this personality is associated with cricket. Now let me search and retrieve all the headlines that belong to cricket. So that is what the embeddings model is capable of. It basically converts your text into a multidimensional vector while preserving its meaning and contextual, the semantic context of it. So we need the embeddings model. Typically, when you are using OpenAI, you would use the text embedding or one of the default embedding models that are available, but there are open source models as well. So in our case, everything remains the same, just like the LLM, but here I use a different container to host my embeddings inference. And again, this is from Hugging Face, a very powerful inference server for embeddings. And the model that I use for the embeddings is the Beijing Academy of AI. They published an embeddings model, which is pretty powerful. It actually topped the MTEB, the massive text embedding model chart, for quite some time. So I'm relying on this to convert my PDF into text embeddings. And everything else remains the same. We are asking for one more GPU. Now, if we do this and if we have exactly one GPU, this pod will be in pending state forever because the existing GPU is already consumed. But in this case, we have two GPUs, so this should go through and we should actually have embeddings model running. So let's go ahead and deploy the embeddings model. So this will basically bring up another pod. And there we go. So now the embeddings is also running. And when we go back and look at NVIDIA SMI, it occupied a part of my GPU. I can technically run multiple models because there is enough space available on my second GPU. So now we have the core building blocks running. Once this is done, next comes in Chroma. Chroma is my vector database. Again, I create a PV and PVC and I put this on my disk, OPT data DB. This is where I basically have the Chroma persisting the data using SQLite. Without going into the details, let's go ahead and deploy the vector database. And vector database doesn't run on GPUs, so we don't really need to care about GPUs anymore. The only two things that matter are the embeddings model and the LLM, and both of them are successfully placed on two corresponding GPUs. So now the vector DB is also created, and then comes in storage. So storage is my data lake. This is where I'm going to keep my PDFs, documents, PPTs, Word documents, unstructured data. So for this, what I do is I basically, again, use my host machine directory. This is where I want to keep my data. And then I deploy what is called as MinIO. So MinIO is a pretty powerful Amazon S3 compatible object storage layer that can run on Kubernetes. So I run MinIO on my cluster and I expose this on a well-known IP address, a static IP address. So let me go ahead and run the data lake, that is the MinIO. And once that is done, we need to deploy the webhook. So the webhook is essentially responsible for taking the PDF, and as soon as the event is triggered, it chunks it into multiple sentences and calls the embedding model. So I will deploy this webhook, and this infrastructure is very, very important. So now what we'll do is we'll deploy webhook. So now the webhook is created, and finally, to bring them all together, I have to connect the dots. How do I tell that? how do I tell WinIO that every time a PDF is added, for this operation, call the webhook. Every time an object is removed, call this webhook. How do I declare that? Well, that's exactly what I do in this job. So I create a job, a run to completion Kubernetes job. And here I basically establish the connectivity between the webhook and the bucket. So my bucket is called PDF or PDFs. And to that bucket, I'm actually saying for every put and delete HTTP request, HTTP event, fire the webhook, right? So every time you add or delete the PDF, so for the event called put and delete and the suffix which is .pdf, invoke the webhook. That's exactly what I do in this job. It's a very, very crucial step where I connect the dots. It basically brings everything together. So let me go ahead and apply the, okay, the webhook is already applied, so that is done. Now comes the job. Okay, so the job is now created. When we look at the pods, the job is completed. When we see the logs, so it basically confirms that it added these webhooks. Every time an object is created, every time the object is removed, and if the filter matches .pdf, it invokes the webhook. So that's what we have accomplished so far. And that completes our entire stack. Now, when I actually do get deploy, you see all these elements. And now coming back to my architectural diagram, well, each of them have been deployed as a microservice or as a deployment. Finally, we need to deploy our chatbot. So let's also do that. So this chatbot is an image that I have built. It's running on Docker Hub. It's stored on Docker Hub. I basically provide all the URLs, all the individual components, like my chatbot knows where to look for the LLM, where to look for the embeddings, where to look for the Chroma database, and it is available on the static IP address. So now the chatbot is also created. When we look at the deploy, it precisely matches. So 1, 2, 3, 4, 5, 6, right? So that's exactly what we have here. These are the exact components that I have deployed on Kubernetes. Now, when we come back and do a refresh of this and ask this question, it says, I don't know. That's because we started with a blank slate. We don't have anything. Now, when I copy my V1 baggage policy to my data lake and ask this question, it is able to respond. So this is basically peeling off the layers and walking you through what went into building a Gen AI platform on top of Kubernetes powered by 2 GPUs. I took a huge risk by VPNing into my lab. There is a human in the loop. I trained my maid on what to do if that machine suddenly stops. She knows to watch the blinking lights of my hard disk, and if that stops, she can reset it and type NVIDIA SMI to check if the GPUs are available. So I have trained her enough. That is what is called putting the human in the loop in AI. So, that concludes my demo. We have ample time for Q&A. So feel free to ask me anything.